Conditional probability example number 2, a nibble. Remember what's a nibble? Half a byte, 4 bits, right? A nibble is randomly generated such that each of the 16 nibbles is equally likely, right? 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0. All 16 of those are possible. Why is it 16? 2 to the 4th, right? Because you have 4 slots for a bit and there are 2 possibilities for each one. What is the probability that it contains at least 2 consecutive zeros given that the first bit is a 0? So how do we think about this? Let's again look at our overall sample space. Now remember, our full sample space is all 16 nibbles, but we're going to narrow that down to a portion of that to be our new sample space because we're doing a conditional probability. So here's our formula again. Did I skip a slide? No, okay, we're good. Here's our formula again, right? So let's look at each piece of this. What is our event? What is E? The probability of E given that F occurred. Do you remember what the question was? So what is E? 2 consecutive zeros, right? Yeah. And then F, here's our sample space here. This is our entire sample space, right? So E is everything in purple. You see that? They have 2 consecutive zeros. It's a total of 8 different things, okay? That's our full event. We want to know the probability of that occurring. Now, if we were just asking the probability of that occurring period, then it'd be 8 over 16, right? Because our sample space is all 16 nibbles. All right. So that's the samples, that's the event set right there. Okay, what is F? What's the given? The probability of E given F. What was F? The first one was a 0, right? Which is all the ones in green. Okay? Which is that set right there. Agreed? Now, with our formula, the probability of getting the green becomes our new sample space, right? That's on the bottom of that formula there, right? So what is the intersection of E and F? Not the probability, just the existence of it. What is the intersection of it? What's those numbers right there? Okay, and you can see that's the same as those numbers there. That is the intersection, okay? Which means that is the sample, that's the event, that's our new event, right? If we go back to our formula of cardinality of E over cardinality of S, right? So if I divide that number by the probability of the green numbers, that's my answer. Now remember, we're dividing probabilities here, so I'm dividing a fraction by a fraction, right? Or a decimal by a decimal, right? So the probability of this occurring is right here, which we decided is 8 out of 16. And then the probability of this event occurring right here, well, what are those? There's 5 things out of 16. The probability of those occurring, 5 out of 16, divided by 1/2. This divided by this will give you this, right? If you don't trust that, do the math and you'll see, okay? Make sense? To the whiteboards. So let's see how this plays out here. Assuming that we have just the choices of male or female, then we have, these are only 4 possibilities, right? You gotta have 2 boys, or a boy then a girl, or a girl then a boy, or a girl then a girl, right? That's it, okay. That's our sample set, the entire set. We're not looking at the given this or whatever. We're just saying this is every possibility, right? Okay. Now, event E. A family with 2 children has 2 boys, right? What is the probability that a family with 2 children has 2 boys, given that, that's going to be our F, that they have at least 1 boy, okay? But our E is the family has 2 boys, because we want to know what's the probability of E given F. All right, so that's our E. Then our F is a family with 2 children has at least 1 boy. So now we have all the variables here, right? We can do this pretty easily. I can convert those into sets, which I think the next slide's going to do that for us. I can put those into actual sets and plug them into this formula right here, all right? So I'm pretty sure the next slide's got the set. Yeah, very good, good. All right, so the E event is there's just that one. That's it, okay? So then we have the F event, which is boy, 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 girl, and girl, boy. There's no girl, girl, because the whole question was, they have at least 1 boy. Do you understand why those are the two sets? What's the intersection of E and F? Just boy, boy. So we put that on the probability of getting just boy, boy, which is what? 1/4, right? The probability of getting this set here out of that, right? That's the number that goes here. 1/4 goes on the top here. Then what's the probability of F occurring? Well, it's 3 out of 4. So you plug in those numbers and you get 1/4 for the top number, as I mentioned, 3/4 for the bottom number, which is equal to 1/3. All right, let's take a look at this idea of independence. A fair coin is flipped 3 times. 1 flip, 2 flip, 3 flips. No bias, just 50-50 chance for either one. All 8 outcomes of a batch of 3 flips are possible. We saw that batch earlier. The given is the first flip was a tail. What is the probability that an odd number of tails appears? That's the exact same question we had earlier. Now I'm adding a new component to it though. Does knowing that the first flip is tails alter the probability that tails will come up an odd number of times? That's the question we want to answer. Let's take a look at that. So in other words, does knowing the event F occurred alter the probability of E occurring? Is the probability of E given F the same as the probability of E? Do you understand why that's the question I'm asking? Is it true that the probability of E given F is the same as the probability of E? If they are the same, then the events are not dependent on each other. If those events are the same thing, then they're independent events. In this case, both of the times will get 50%, which means that they are independent events. In the, pardon the use of the word event again here, but in the event that they are not equal to each other, then that means that they are not independent, that they are connected to each other, right? And so that the probability of E given F is different than the original probability of E. That's the idea. So let's look at this a little bit more generalized here. If 2 events are independent, then the probability of E given F is the same as the probability of E. Now we know this formula to be true, right? We've just studied that for a few minutes. So if that's the case, then I could swap out this for this, right? If this is true. Agreed? Thus, events E and F are independent if and only if the probability of E times the probability of F is equal to the probability of the intersection of the two. Just algebraically rearrange that third bullet point. If you algebraically rearrange this, you will get this. So if the probability of event E is true, if the probability of event E times the probability of event F is equal to the probability of the intersection of the two, if that is true, then these are independent events. So let's let E be the event that a randomly generated nibble begins with the number 1. Let F be the event that the nibble contains an even number of 1s. This is a different problem than before. If all 16 nibbles are equally likely to be generated, are events E and F independent? That is the question. So let's take a look at how we would approach this. Here's our set. This is our sample set right here. That's every single nibble that can be generated. The question is that true? Is the probability of E times the probability of F equal to the probability of the intersection of the two? Well, what's the probability of E? What is E? Yeah, so the probability of that is what? 1/2, right? 8 out of 16. And we reduce it down to 1/2, obviously, but I like to put the whole numbers there at first so we can see where the numbers are coming from. What's the probability of F? It's that it contains an even number of 1s. That one's a little trickier. You have to count them up, but the answer you'll see, it's all of those guys. So that is also 8/16. So now what's the probability of the intersection? The intersection is 4/16, and we can see that because this is event E, all of the reds are event F, but the intersection is only these red ones inside of the blue there. That's the intersection, which is 4 out of all 16. The probability of getting any one of those that are an intersection is 4 out of 16. So the question is, are they equal to each other? That's what we're trying to figure out. Is 8/16 times 8/16 equal to 4/16? Let's reduce it down to 1/2 times 1/2. Is that equal to 1/4? And the answer is yes. So these are independent events. In other words, what does it mean to be an independent event? The probability of E occurring is the same whether F occurred or not. That's all it means. That's an independent event. So my question originally is, what's the probability of E given F occurred? Well, it's the exact same probability of E occurring whether F occurred or not. That's when they're independent. Now, if the probability of E given F differs when F occurs, then we have dependent events, okay? To the whiteboards. So the first question, well, I've laid out all the variables for you, right? Event E is a family that has 2 children, has 2 boys. Event F is that the same family has at least 1 boy. Assume each of the possibilities of having 2 children are equally likely. Are the 2 events independent? That's question number 1. We'll take a look at that one first. These are our sets here, right? Let's just make sure you agree with them. Your event E is that they have 2 boys. That's it. 2 children and they're both boys. Event F is that we have 2 boys, we have a boy-boy or a boy-girl or a girl-boy. Make sense? That's event F. This is the same problem we did earlier, right? So now what is probability of E, probability of F, probability of intersection of E and F? What are those values? And we see that they are 1/4, 3/4, and 1/4. The question is 1/4 times 3/4 equal to 1/4? That's the question. The answer is they are not equal to each other. So Craig, this goes to your question earlier. Because they're not equal to each other, they are not independent. These are dependent events. In other words, the probability of E given F is different because F occurred than it would be if I just want to know the probability of E. It's different, right? So in this event, basically I'm asking, what's the probability of E given F? Whatever that is, it is different than just the general, whatever the probability of E on its own is. Those are different probabilities. Probability of having 2 boys is different given you have at least 1 boy. And that kind of makes some sense, right? Question number 2. Event E is the family has 3 children. They have 3 children, both sexes are included. Event F is the same family has at most 1 boy. All 8 possibilities are equally likely. Are the events E and F independent? Look at our universe. That's every possible combination there, right? Look at our event, E. A family with 3 children has children of both sexes. So we can't, basically we've eliminated boy, 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 and girl, girl, girl. Yeah? Okay. Last one, F. They have at most 1 boy. Well, that means boy, girl, 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 boy, girl, 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 boy, or girl, girl, girl. There's no where there's 2 boys. They have at most 1. So 0 or 1, basically. So now, what are those values? What's the probability of E? Well, what is the probability of E? It's whatever that is 7 divided by that number there, which is 2, 4, 6, 8. Right? Did I count that right? 2, yeah, 6/8, thank you. Yeah, I just counted wrong. Okay, what's the probability of F? Well, it's 4/8. So the numbers, if you plug them in, you get 6/8 times 4/8 and 3/8 for the intersection, right? And those are equal to each other. So these are not dependent. So here's what this means. You ready? The probability of E given F is the same as the probability of just E, all right? All right, this is where it starts to get crazy, okay? If it wasn't crazy enough. Bernoulli Trials, let's start with a basic, simple idea. Here's what a Bernoulli trial is. It's any experiment that has only 2 possible outcomes. What are some examples of that? Coin flip, heads or tails, right? Okay? We refer to them as a success or a failure when we're talking about a Bernoulli trial. Rolling a die is not a Bernoulli trial. Now, I'm not talking about what are the favorable outcomes. I'm talking about the entire possible outcomes. In other words, when your sample set is only 2. That's what I'm talking about. And we refer to it as a successful trial or a failure, right? Now, if we say that P is the probability of success, and we say Q is the probability of failure, then what do we know about P plus Q? It equals 1. Yeah. A lot of problems can be solved by determining the probability of some number of successes of n number of mutually independent Bernoulli trials. That's a mouthful there. Let's look at what that means, an example. So let's say we have a coin is biased. That should be a D, not an S, but I'm not changing it. A coin is biased so that the probability of heads is 2/3. So 2/3 of the time you flip this coin, you're going to get heads. What is the probability that exactly 4 heads come up when the coin is flipped 7 times? K successes out of n trials, out of n Bernoulli trials. Even though this is a weighted coin, you still have 2 possibilities, heads or tails. So assume all the flips are independent for this. What are the possible number of outcomes? It's 2 to the 7th, right? Why is it 2 to the 7th? Yeah, you can only have two heads or tails for each one of the 7 times, right? So 2 to the 7th is 128. So there are 128 possible outcomes. What are the number of ways 4 flips can be heads when we're dealing with 7 possible flips?
7 choose 4.
7 choose 4, very good. So if I have 7 possible flips, right, I'm going to flip the coin 7 times. Any 4 of those 7 could be heads. And I'm looking at all the events where only 4 are heads. Well, how many different ways are there to do that? 7 choose 4. For each of the above 7 choose 4 ways, the probability of heads occurring is 2/3 of the time. So each of those 4 ways that I have a head, the probability of me actually getting that head is 2/3. Do you guys agree with that? That's just our original example that we were given. And the probability of the tails is 1/3. Okay, that being the case, here we go. This is the final probability here. There are 2/3 to the 4th power because we're talking about 4 successes, and the probability of getting a success is 2 out of 3 times, times 1/3, that's the other 3 that are tails, right? The probability of getting a tail is 1/3. Plus, that can be done 7 choose 4 different ways. You multiply all that out, and you could do the math yourself, you're gonna get about 25%. I'm less worried that you can do the math. I think we can all do the math, right? My question is, do you understand why that's the formula? So let's kind of generalize this a little bit, and you're gonna see something that's gonna be familiar, I hope. This is our formula we just had on the previous page. That is raised to the 4th and raised to the 3rd. I know my superscripting is a little off there, but that is what that's supposed to be. Now remember, we'll say that n is 7, right? That's the number of Bernoulli trials, and a Bernoulli trial is just a binary choice, heads or tails, 2 possible outcomes. K is the number of successes, right? So I wanted to know K successes of n trials, right? That's what I was asking. We know the probability of success is equal to P, and the probability of failure is equal to Q. These are all generalizations. I've just plugged in the number 7 and 4 to show you how they fit in our formula. But let's do a little bit of plugging and playing here. We also know that Q is equal to 1 minus P. All those are known things, right? We get that? So, that being the case, look at our formula here. Does this look familiar? It's the combination, or the 7 choose 4, or n choose K, times the probability of success, which is P, raised to the kth power, the number of successes, times the probability of failure, Q, raised to the n minus k power. Do you agree with that? The generalized formula there? What's that look like to you? Okay, it'll come to you in a minute. I'll save the surprise. You saw it. Hold that thought. Okay, here's how we write this. If we want to know that little b for Bernoulli, which is named after, I think his name was James Bernoulli, guy who came up with this idea. What I'm saying here, in my formula, or my little way of denoting this, I want to know for a Bernoulli trial, k successes out of n trials where p is the probability of success. That's what that variable is, that little formula is all about, that little notation, if you will. So let's take a look at this, and we'll see this in action with some pictures in a minute. Suppose the probability of a 0 bit being generated is 90%. Whatever, we have some program that generates a 1 or a 0, 90% of the time it generates a 0. Therefore, the probability of a 1 is obviously 10%, right? What is the probability that exactly 8 0 bits are generated when a total of 10 bits are generated? When we generate 10 bits, 8 of them will be a 0. All right, so if we look at our formula here, this is what I'm asking. I'm asking for a Bernoulli trial. I want to know what 8 successes out of 10 where the probability of that success is 90%. That's what I'm asking. Using our formula there, we understand that? 10 choose 8 times the probability of success, 90%, raised to the 8th power because I want 8 successes, that's what I'm looking for, times the probability of failure squared, because there's only going to be 2 failures if we're looking at a total of 10. And that will equal 19% chance. Why does that seem low? It's correct, but why does it seem low, 19%? To me, it seemed low because the probability of getting a 0 is pretty high. It's 90% of the time you're going to get a 0. So why is getting 8, only 8, so low? because you're probably gonna get 9 or 10. You're probably gonna get a lot more than that, right? Or as many as you can get, because the probability of getting one is so darn high. So the probability of only getting 8, in fact, the probability of only getting 1 is probably crazy low, because 90% of the time it is gonna be a 0. Make sense? So now let's look at a picture of this to help sort of solidify this. The idea of this concept is this. I've got 10 bits total that are gonna be generated. 8 of them are gonna be successes. I wanna know what the probability of that happening is. So if we say that those are the 8 that are gonna be successes, okay, fine. The probability of me having a success there is 90%. Probability of me having a failure, 10%. So we can multiply, that's the green ones are 0.9 times, they're to the 8th power, and our purple ones are 0.1 to the squared. But I can rearrange them this way, right? I could also rearrange them that way, right? I can rearrange them 10 choose 8 ways. So there are 10 choose 8 ways to have 8 zeros. That's where we get this formula from. Let's generalize it a little bit further here. Let's let n equal 2 trials, 2 Bernoulli trials. We'll let k equal 0 successes. Would you agree that that's the formula for figuring that out? That's just me plugging and playing that first bullet point in there, right? That's a 2 minus 0 there. That's just due to the nature of superscripting, it looks a little wonky. Let k equal 1 success. Let k equal 2 successes. Well, it's that, right? Agreed? So thus, in the case of n equaling 2 and k equaling 0, if I increase each time, the probability of getting 0 successes plus getting 1 plus getting 2, that will equal 1. Agreed? Because that's all the possibilities, because I'm going to have an n number of trials. Does this formula look familiar? In other words, the sum from 0 to n is this formula here, n choose k times the probability of success to the kth power times the probability of failure to the n minus k. All that summed up will equal 1. That's the binomial theorem right there, which we then also know that it's equal to p plus q to the nth power. That is what the binomial theorem states, right? So how do we feel about that? Any questions about the idea? We're going to apply it now in just a moment. Here is this idea of a random variable. Well, I told you that's neither random nor variable. It's just a function. So let x of t be a function that equals the number of heads that appear when t is the outcome. For example, if I have and we're doing 3 flips here, I forgot to mention that. Possible values of t, we have, what I'm saying here is that this t right here is going to be one of those things, one of these, right? And this function will calculate the number of heads that occur. So if I pass in this value here, then this function will spit out the number 3. If I pass in this value here, that function spits out the number 2. Okay, that's all that this is doing. So it's just a function that's going to, we pass in the total outcomes, and it'll give us the number of heads or whatever we define the function to be. So it evaluates the count of heads, as I just pointed out. So in other words, this is what we get. Does that make sense? Assuming I don't have any typos there, that should be correct. In other words, look at this. Would you agree that that is the same thing as that? I'm just matching up the equals, right? So in other words, these 3 are all equal to 1. These 3 are all equal to 2, right? So I'm just cleaning it up to put them all in the same line. Interesting looking pattern, isn't it? Does the pattern seem a little familiar to you? Turn it sideways, 90 degrees to the left. It's normal distribution, isn't it? That's not a coincidence. Let's see how this plays out. We don't do a lot of whiteboard stuff with me using the markers in this class because of all the PowerPoints. But early in the class before we switched to PowerPoints, my marker dies, I toss it in the garbage can from across the room, and my memory of my free throw percentage is at 70%. I'm gonna guess you guys don't agree with me on that at all. That's my false memory. We're gonna go with my memory of that. So my dead marker free throw percentage is 70%, okay, which means my miss percentage is 30%. If I throw 6 markers away, what's the probability that exactly 2 of them will make it? Well, let's look at how this would play out. There's 6 tosses, and exactly 2 of them, each one of those, there's a 70% chance that it'll go in, that I'm gonna have that success rate. And there is a 30% chance that I'm gonna have a fail, assuming my numbers are true, which they're not, obviously. What would you say my real percentages are? I'm just curious.
I think they're split.
The other way around, 30-70, yeah, probably. All right, we're gonna go with this though anyway, okay? All right, so now we get this, right? We agree with that idea? That's what we've been looking at all this whole time. But if I wanna do all of them, this is what it looks like. Now, this is with some weighted probability here. The formula still works, it still applies. If you sum those up, it will be 100%. Okay, let's look at a situation where it's not weighted. The probability of getting 0 heads, or 1 head, or 2, or 3 and so on. Just like before, I was looking at the probability of getting no shots, or 1, or 2, or 3, or 4, or all 100%, or all of them, right? It's a 100% chance that I'll get one of those. So in this case, we're flipping a coin 5 times. And I want to know the probability of me getting 0 heads, 1 head, 2 heads, 3 heads, 4, 5, and that's it, okay? Would you agree with my formulas on the screen? And the calculations are correct, I did them. Do you see anything interesting there? Look at the pattern in the numbers, in the final numbers, the percentages. Turns out that that's the equivalent of n choose k divided by 32. N choose k divided by 32 will give you those values right here. So 32 is 2 to the 5th, because we have 5 flips and there's 2 possibilities, right? So if I simply take n choose k and divide it by 32, that will give me the probability of me getting k, right? So in other words, this. If we use Pascal's triangle, right, 5 choose 0 is 1, 5 choose 1 is 5, and then 10, and then 10, and then 5, then 1, right? Remember that from the triangle, right? So if I do 1 over 32, that is that. If I do 5 over 32, that is that. And I do 10 over 32, that is that number. That ends up being the same thing as just calculating it this way. They're both the same. So if we're dealing with, this is a non-weighted event here, equal probability of getting one or the other. If I were to draw out 5 blank slots and I want to know all of them are heads, 4 of them are heads, 3 of them are heads, 2 of them, 1 of them are 0, it will be the equivalent of 5 choose 0 divided by 32, 5 choose 1 divided by 32, and so on down the line. And you will get this normal distribution looking value, and you will get the final answers there. How do we feel about that idea?